Good day and welcome back for part 2 of our discussion on volumes using cylindrical shells. So a reminder from last time, if we have a region enclosed underneath a curve given by the graph of a function f of x, and we form a solid of revolution by rotating that region about the y-axis, then its volume can be represented by the definite integral from a to b of 2 pi x f of x. And what I would like us to focus in on is the form that we see here, 2 pi something something. That first something is representing the radius of one of our shells, and the second thing, f of x, is representing the height. And how we form a shell in this case is we pick a value of x between a and b, and we draw a small vertical line segment between that x value and the curve. And then when we rotate that line segment about the y-axis, we form what we think of as being a shell. The height of the shell is determined by the function value at x, and the radius of the shell is simply equal to x in this scenario. But note, if we understand intuitively how we set this up, we should be able to modify the scenario for, say, rotating around different lines, both vertical and horizontal, as well as dealing with regions enclosed by two curves instead of just one curve in the x-axis. Let's move on to a typical example. Set up an integral that represents the volume of the solid obtained by rotating the region bounded by the curves y equals square root x, y equals 0, and x equals 1 about the line x equals minus 1. So our region in this case is bounded by the curve y equals square root x equals 1, and y equals 0. And we are going to take this region and we are going to rotate it about the line x equals minus 1 to form a solid of revolution. And immediately, since we're talking about using cylindrical shells, we know precisely what our setup is going to look like. The volume is going to be given to the definite integral, in this case over how the x values vary, 2 pi something something. And remember what those quantities represent. The first something is representing the radius of our cylindrical shell, and the second something is representing height. So let's just sketch a typical shell. If we pick our favorite value of x between 0 and 1, and we draw this small vertical line segment, and we rotate that about this line, x equals minus 1, we graphically have a representation of our shell. What we need to think about is what represents the height, what represents the radius. And note, in the picture we can see the height is given by the function value at x, and that function value in this case is the square root of x. And the radius of the shell is the distance this x value is to the line we rotate about. So in this case, that radius would be x, the bigger value, minus the coordinate of that smaller value, minus 1. So this would be equal to x plus 1. And that would be the radius of our shell. And note the key intuition here when you're determining the radius. We want to go from this x value to the line x equals minus 1. So we take the bigger number x, and we subtract away the smaller number minus 1, and that tells us the radius of this shell. And note, for this problem we are simply asked to do a sit-up, which we've done, so now we would stop and go on to the next problem. But in this case, just for fun, I want to take this a bit further and say, what if instead we rotate about the line x equals minus 2 or x equals 2? In either of those cases, or actually in both of those cases, I would like you to pause the video and write down the definite integral, much like we've done above, to represent the volume of that solid of revolution. And it should be a quick, simple, one thing that needs to change. Okay, so hopefully you've taken a minute to think about this. So now if instead we want it to rotate about the line x equals minus 2, our integral still has this same basic form. The region we're dealing with ranges from 0 to 1. That determines the bounds of the integral. And the form is going to be 2 pi something something. And note, regardless of the vertical line we rotate around, it's going to take precisely this form. All we need to do is just think, how will that cylindrical shell change? And let me go ahead and draw the shell in the x equals minus 2 case. If I want it to instead rotate about this line x equals minus 2, and hopefully this doesn't complicate the picture too much, we would take this same starting point, but now all of a sudden our shell would just become a bit wider in a sense, right? And let's pretend this is fully to scale. I didn't quite have as much room as I wanted. So the height remains unchanged. It's still the square root of x. What is going to change is the radius of this new yellow cylinder. You have to go from x all the way to minus 2 now. So that radius would be x minus a minus 2, or x plus 2. And if you instead rotated about the line x equals 2, the idea would be the same. The height of the cylinder is unchanged, but now if you're rotating around the line x equals 2, the radius of that cylinder would be 2 minus x. And I'm not going to draw it in. I'll leave it to you to think about it if you're unsure, but it's a subtle difference in the setup. Now that we've investigated several examples related to rotating around a vertical line using the method of cylindrical shells, let's flip it around and see if we can do the same type of problem with instead rotating around a horizontal line. And that brings us to another very typical example. Let's find the volume of the solid obtained by rotating the region bounded by the curves y equals square root x, y equals 0, and x equals 1 about the x-axis. So note, for simplicity, we are going to take the same exact region that we had a moment ago. We're bounded by the curve y equals square root x equals 1, and y equals 0. And we are going to form a solid of revolution by rotating this about the x-axis. And let me just note the intuition here. We could certainly take care of this using the washer method. And let me just kind of remind you for fun how that works. For the washer method, if we pick an x value between 0 and 1, think about breaking this region into vertical slices, and you draw a vertical line segment. When you rotate that vertical line segment about the x-axis, you form kind of the ideal washer. It's just a circle. And the radius of this circle, or washer, is the square root of x. So the volume is the definite integral over how the x values vary, in this case 0 to 1, and we integrate the area of that cross section at x, which in this case would be pi times the radius squared. So a very quick, efficient example using the washer method. Let's now investigate this same problem in terms of the sit-up, but we're going to do it using cylindrical shells. And I know you might be looking at this and saying, well, if we can do it one way, why in the world would we care about doing it another way? And the reason is, the more perspectives or different points of view you have on a given problem, in general, the better off you are going to be. It gives you options. So to use the shell method, what we are going to do is break it up in horizontal slices instead of vertical slices. So if we pick a y value between 0 and 1, and we draw a small horizontal line segment corresponding to that y value in our region, and we rotate that about the x-axis, what we form is our typical shell. This should look familiar. So in this case, if we set this up using our procedure, it's going to be a definite integral of 2 pi something something. Now note, because we're breaking it up into these horizontal slices, we're breaking up along the y-axis, so that gives us our variable of integration. Our y values in our region vary from 0 to 1. That gives us our limits of integration. What we need to think about is the radius and the height. And this is where we need to be careful. So the radius is simply y. The height is going to be the height of this shell. And remember, we always take the larger quantity and subtract away the smaller. And as functions of y, bigger is determined by further to the right. So in this case, we have x equals 1 is the rightmost side of our region. So that's the bigger curve. And we need to subtract away the smaller curve. Well, if y is equal to the square root of x is equal to y squared. So the height would be 1 minus y squared. You're going from the larger value here, x equals 1, we subtract away the smaller curve, x equals y squared. And both of these integrals will allow you to determine the volume of this solid of revolution. And I'm not going to go through the actual evaluation because these are fairly, hopefully at this point, quick and efficient definite integrals to evaluate. Instead, I want to make more of a bigger picture observation. So I have the following note to make. With cylindrical shells, what we have seen in our last two examples is if we rotate around a vertical line, so the example we started with in this video, we need to deal with functions of x. So it's kind of an ideal scenario. Whereas with the washer method, if you just kind of picture what a washer would look like, when you rotate around a horizontal line, you have functions of x. But what we see in our picture above is that when we rotate about a horizontal line, using this method of cylindrical shells, we are going to be dealing with functions of y. So that completes our current video. We will move on and explore more examples in the next video. But as usual, let me note that this is most definitely a topic that requires extra practice. The more you practice, the easier, the quicker, the more efficient the setup and the evaluation of these integrals will become. So let me know when you have questions, and stay tuned. Take care.